Hello. Today we'll be talking about the plane stress problems, and we will be driving the first two-dimensional finite element. So the plane stress is a special case when you know that the stresses in the z direction is equal to 0. This is the case where we usually see in slabs or walls that undergo in-plane deformations, and since the two dimensions when compared with the thickness is very large, we can ignore the stresses in the in that small dimension. So let me draw a 2D body. So it has a certain thickness. Let's call this axis as X. So we have the y-axis here, and that would be the z-axis. And we are saying that this member can have stresses in the xy plane, in the in-plane directions, but the stresses in the z direction is equal to 0. So if that's the case, if we are looking only the stresses, uniform stresses in the xy direction, we can idealize that member as follows. So we can just take the mid-surface of it, that will be the x direction, so that will be the y direction. So we have a two-dimensional element. We idealize an actual three-dimensional member with a two-dimensional element. By taking a section at the mid-surface. So in that case, the third dimension is represented as functions of x and y, and are integrated through the plate thickness. So basically what we are doing is we are just representing a member has some depth, but the depth is very small when compared with the other two dimensions. We idealize it by a single two-dimensional element by considering only the mid-plane. So we have a surface, that's our plate domain, and we have a plate boundary. So let's define the stresses and the forces on this member. So in order to do that, I'll take a small infinitesimal element here. So let's show the forces and stresses. So let's draw that infinitesimal element here. So that's y, that's the x-axis. So the definition of the stress is as follows. So we assume uniform stress in the x direction. So these stresses are called sigma xx. Assume uniform stresses in the y direction. These stresses are called sigma yy. And we also have stresses, shear stresses as follows. So we are assuming that all these stresses are constant with respect to the depth of the member. So you can just think of this formulation as the 2D version of a truss element. So here we are only considering the axial deformation. So this stress is called sigma xy. So x, the first label x represents the face, and the second label y represents the direction. So this stress is sigma xy and this stress is sigma yx, and we can say that sigma xy is equal to sigma yx. So our in-plane stresses are as follows. We have stress xx, stress yy. So these are two axial stresses, and we have a shear stress. Now these are the stress definitions on this 2D truss member. So we no longer, of course, call it 2D truss member, but we call this type of elements as membrane elements. So let's show the forces on this membrane element. So again, this is our infinitesimal element. We have y-axis here. This is the x-axis. So we have the integrated version of this stresses on this infinitesimal element. This is fxx. So we have fyy here, and we have the shear forces on this infinitesimal element. This is fxy and this is fyx. So the internal forces for this plate element is fxx, fyy and fxy. So these are the membrane forces. So axial forces in 2 dimensions, we call them membrane forces. And we can easily calculate the membrane forces by multiplying the stresses with the thickness of the member. So this is the thickness of that membrane element. So one important note here is these forces. We have these internal forces, and remember that these forces are defined for an infinitesimal element. Okay, so their units are different than the forces that we know for the one-dimensional elements. The units are, let's say that the force, the kilonewtons per unit length. Okay, so there's also a per unit length as units on these internal forces. Remember that according to this definition, they are defined for an infinitesimal element, or let's put a note, we can just say that these forces are defined for a unit length. So that's very important. You cannot just directly use these forces to design a structure. You have to take a tributary with and integrate that forces and get your design forces, because again, let me repeat one more time, these forces are defined for a unit length. So these are the force side. Now let's take a look at the displacements now. So they are assumed to be uniform through thickness. Okay, so we have a uniform displacements. So the in-plane displacements are defined by two components. So our displacement field is defined by displacement in x direction and displacement in y direction. Okay, no rotations are defined. But this doesn't mean that we don't have any deformation or displacement in the z direction. So the deformation in z direction is non-zero. Why? Because of the Poisson effect. So what we are saying is, in this type of element, in this membrane elements, the membrane element can deform in the in-plane directions. Okay, it can move in the in-plane direction. Of course, due to that in-plane deformations or the displacement, we will see a deformation in the z direction, but this deformation is not due to the applied loads, but it is due to the Poisson effect. Okay, so this is a two-dimensional version of a truss element, and it can only resist forces in its in-plane direction. That's what we assume when we formulate a membrane element. Of course, the theory, according to the membrane element, we have ux and uy, but as we will see in some formulations, the rotation in z direction is also considered. This rotation, usually short as theta z, is called drilling degrees of freedom. So let's take a look at the strains now. In-plane strains for the plane stress case are defined as follows. So this is our strain vector. So we have an axial strain in the x direction, axial strain in the y direction, and we have a shear strain that represents the angle change. So in order to formulate this element, we will follow the procedure that we always do. We will relate the forces with the stresses. Now here is the relationship. Now I need to relate the displacement with the strains, so that displacements and strains are related by kinematic equations. And strains and stresses are related by constitutive equations. So what we are going to do is, again, we have the force-stress relationship. I need to find a relationship between the displacements and the strains, and then we need a relationship between the strains and stresses. So after determining all these relationships, we can write down the energy equations and obtain what we need to do to calculate the stiffness matrix and the consistent load vector. So let's do that, okay? Let's start with the kinematic equations. So for that, I'm taking one of the edges of that infinitesimal element. So that's 0.0, that's 0.1, and that's 0.2. So the length of 0,2 is equal to dx, and the length of 0,1 equal to dy. Okay, so let's say that this 0.0 moved by this amount v, and also in the x direction it moved by u amount, and it moved to this point. And also let's say that it experienced some angle change, so let's also show that. Oops, let me draw it this way. So this is 0.0 prime, 0.2 moved here, 2 prime, and this is 1 prime. So basically 0.0 moved from 0 to O prime, okay? So the translation of 2, let's show that. That's the translation of 0.2, and this translation can be written as follows: u plus the change of displacement with respect to the x-axis multiplied by the length of your member, which is equal to dx. So change of displacement with respect to x multiplied with the length of the member gives me the x coordinate of the 2 prime. Now what about 0.1? So it was here before, and then it moved to this location. So this displacement, let's do it right here, u plus change of u with respect to y multiplied by the length of the member will give me the new location of 1 prime. So let's do the same thing for the displacement in y direction. So point 1 move in the upward direction by this much. Okay, and this translation, let me do this so that I can write it better. Let me move this in here so that we'll have more space. Oops, sorry. All right, let's continue. Now point 1 was here before and it moved in the upward direction by this much. So if I write it in equation form, v plus change in displacement in the vertical direction with respect to y multiplied by the length of the member, which is dy. And for point 2, this displacement is v plus the change of vertical displacement with respect to x multiplied with the length of the member. And we have the angle changes, so let's plot that. So this angle is now, let's call this one beta 2 and this angle as beta 1. So here I show all the changes, right? Initially our element was here, that infinitesimal element, that corner. This is dy and dx, and due to some deformation, point O moved to point O prime, 2 moved to 2 prime, and 1 moved to 1 prime. All right, and the displacement in point O is equal to u and v. Now the horizontal displacement of 2 is equal to u plus change of horizontal displacement with respect to x multiplied with the length of the member, and the vertical translation of 2 will be v plus the change of vertical displacement with respect to x multiplied with the length of the member, and you can write the same equation for point 1. Now let's use engineering strain definition. So we are here assuming that the strains are small. Let's use engineering strain. So the axial deformation in x direction will be equal to length of O prime 2 prime minus length of O2 divided by the original length. Okay, that's the strain in x direction. So that's equal to, what is the length of this member in x direction, how much its length change in the x direction. So I can write the length of O prime 2 prime as follows: dx plus u plus del u over del x dx minus u will give me the length change in x direction, right? So this point, the new coordinates of this point is equal to dx plus this one. That will give me this length. Do we all agree? If we agree, then I have to subtract the length of O2, which is equal to dx divided by the length of member LO2. So from that, we see that these u will cancel, these two will cancel, these two will cancel, and I end up with the following equation: epsilon xx, the axial stress, is equal to del u over del x. Alright? So that's our displacement strain relationship in the x direction. And we can write the same equation for the right y direction. So in a similar manner, we can obtain epsilon yy as equal to del v divided by del y. So these are the axial strains. Now let's take a look at the shear strain. So the shear strain is amount of change by definition, right? Amount of change from right angle. And we can show it by gamma xy. So if we assume for small rotations we can write the following: tangent beta 1 is equal to beta 1, okay? And let's not use gamma for end. And I can write the same thing for tangent beta 2 as equal to beta 2. And the change in right angle is actually the summation of these two angles, beta 1 plus beta 2. So with all this information, I can write the following: the shear strain is equal to beta 1 plus beta 2, and we know that we can take beta 1 is equal to tangent beta 1. So let's take a look at beta 1. It is this distance divided by initial length dy. So that distance is equal to u plus del u over del y dy minus u. Okay, so again, let's repeat what this is, where what I'm trying to calculate. So it's equal to this distance, that one, minus that one, which is equal to u, divided by the original length in the y direction. So we are saying that this distance is equal to dy. Plus, for beta 2, I will use this distance. So that's equal to v plus del v over del x dx minus v divided by this length, and we are taking this length as equal to the initial length. That's equal to dx. So in that case, these u will cancel, dy will cancel, v's cancel, dx will cancel, and I obtain that shear strain as equal to del u over del y plus del v over del x. So my my kinematic equation, or the strain displacement relationship, if I show it in matrix form, is as follows. Axial strain in x direction, axial strain in y direction, and shear strain is equal to del over del x 0, 0, del over del y, and I got del over del y and del over del x multiplied with u and v, and that's our strain displacement relationship. Now let's take a look at the constitutive relationship. That's the relationship between the stresses and strains. So for an isotropic material, and plane stress conditions, we have the following relationship: sigma xx, sigma yy, and sigma xy is equal to elastic modulus divided by 1 minus square of the Poisson ratio 1 mu 0 mu 1 0 0 0 1 minus mu divided by 2, and we have here epsilon xx, epsilon yy, and epsilon xy, and this usually shown by stress is equal to constitutive relationship or the material matrix multiplied by the strains, and that E is called constitutive relationship matrix. So how did we obtain this relationship? You are using the Hooke's law, the generalized Hooke's law for 3D, and then you write down the following condition: theta zz should be equal to 0, and then relate these stresses with the strains, and you end up with the following relationship. So before going into the energy calculation, let's repeat what we did. So here our aim is we have a 2D truss member. In other words, and it's called a membrane element, or we can just say that the membrane element resists axial forces in two directions. And we call these directions as the local X and Y directions. And we say that, okay, that we'll consider this as a plane stress problem. So we are assuming that the stress in the Z direction is equal to 0. You can actually formulate that problem as a plane strain problem. So let's imagine that you have an infinitely long domain and you take a slice from that domain. Since the domain is infinitely long, you can just say that the strains in the Z direction is equal to 0. Then this problem would be a plane strain problem. Now here I just consider it as a plane stress problem because we usually see in many of the in our structures we solve as a plane stress problem, and in that problem we are assuming that the stresses in the Z direction is equal to 0. So we have a two-dimensional element, right? The dimensions of the actual member in these two directions is much longer than its dimension in the Z direction. So that's why we can idealize it as a two-dimensional element. And this surface is defined at the mid-surface. And whenever we need to do something with respect to depth, we integrate it. We use the integration. Now in this membrane element, the stresses are defined as uniform, and we have three types of stresses: axial stresses in X direction, axial stress in the Y direction, and the shear stresses. And usually the labeling of these stresses as follows. The first component represents the face, so this stress is at the face X and the direction is X. Now these are the stresses. Now I need the relationship between the force and stress. So the forces is simply calculated by multiplying the stresses with the thickness of the member. But remember that these are not the stresses that we are used to in the one-dimensional elements. These forces are not the same forces as we see in the one-dimensional element. For example, in a truss element you have a force, right? The axial force of the truss. But in a membrane element you have forces in X, Y, and the shear force, and these forces are defined for a unit length. You can directly design a truss by taking its axial force. So in order to define a member like this, you have to calculate the internal forces as follows. Take a tributary width on the actual member and consider the variation of the force, integrate it, and this integrated force must be used in the design. So that's our force stress relationship. The next thing is to take a look at the displacements. So in the membrane elements we actually have two types of displacement: translation in X direction and translation in Y direction. No rotations are defined, so in the membrane element these are the two displacements that we will see, and in the future we will see alternative displacement with the rotational degrees of freedom. The reason of showing these two displacements is this. Now when we try to relate the displacement with the strains, you will see that these strains, the axial strains, occur only due to the translations, not due to the rotation. Okay. Now for this type of member we have three strains: axial strain in X, axial strain in Y, and the angle change, which is called the shear strain. Now in order to move forward, I need to relate the displacement with the strains, and I need to relate the strains with the stresses, and this is usually the steps that we follow in a finite element formulation. Now the first step is the kinematic equations, displacement relationship with the displacements and the strains. Here we have two assumptions. We use engineering strain, right? So deformation divided by the original length, and this is the axial equation for the axial strain. This is again an equation for the axial strain in y direction. While calculating the shear strain, we assume a small rotation. We take tangent beta equal to beta, and while calculating this beta, again the deformation divided by the original length, and we obtain the following equation. And here we have the relationship between the strains and the displacements, and as you see, there is no drilling rotation here. It's not in this relationship. And as a final step, we relate the stresses with the strains. For that, we use isotropic material and plane stress conditions. And when you use the Hooke's law with these two assumptions, this is what you will get. If you want to solve a plane strain problem, for example, then you will have a different constitutive relationship here. Anisotropic material, orthotropic material, so this part will be different. Anisotropy, I don't know, but for the orthotropic, this part will be different. Now, in order to continue with the finite element formulation, we have to write down the energy equations, and then from the energy equations we will figure out the trial functions and do the finite element formulation. Now let's calculate the total potential energy functional. Potential energy functional. So we are saying that the internal strain energy, of course I'm doing it for a single element, is equal to, so the total potential energy is equal to internal strain energy minus the external work. So the internal strain energy, we can start from the very general equation, integrated over the volume, 1/2 force at an infinitesimal element multiplied by the strain on an infinitesimal element, and integrated over the volume. So for the volume, since we simplified it, I can write the following: integral over the surface 1/2. Instead of stress, I can write elastic, or E, multiplied with the, let me do it this way, strain multiplied with E multiplied with strain. T times ds will give me the d volume. So that's the expression for the internal energy. So if I write it in matrix form, so we have the strains in matrix form and the matrices, the constitutive matrix in matrix form, then that will give me strain transpose multiplied with the constitutive relationship multiplied with the strains itself. T times ds will give me the volume. Now the external work can be calculated as follows. Let's use the surface integral. S, we have a surface load, a body load, multiplied by the displacement transpose itself, so that we'll get a volume T times ds. So if that's the case, if we have a body force plus if we have a surface force or the boundary force, that's the way we will calculate it. T times ds. and that will give me the external energy. Of course, this should not be S, this should be the boundary. So here this one represents the body forces, and this one represents the boundary forces. So when we look at this, the force to work expression, so we have the displacements itself. So let's take a look at the internal strain energy. So here I have the strains. So let's take a look at what we have for the strains. So for this purpose, I'm looking at the strain displacement relationship. Strain expressions has the first derivatives of the displacements. Okay. So let's put it as a node. The total potential energy functional has first order derivatives of u. So in other words, this means that the degree of the total potential energy function is equal to 1. It has only the first order derivatives of u. So from that we can just say that any trial function with C0 continuity is an admissible displacement interpolation. Okay, so what we learned from this derivation is we can use any interpolation function with C0 continuity. I have the relationship between the stress and strain. I have the relationship between the strain and displacement, and I have the expressions for the internal strain energy and also the external energy. So basically now we are ready to formulate our first two-dimensional membrane element.